Hello, everybody. Today we continue generalization of Skorokhod reflection problem. Let me recall briefly the notion of generalized Skorokhod problem. So we have a function w which will be continuous, and f cadlag and strictly increasing. We assume that function w start from the non-negative point, and we wish to find a pair x of t and L of t such that x can be represented as w plus f of L of t, where x is Cadlag function, non-negative, and L is non-decreasing, and L may increase only when the process x is at 0. So L does not increase when the process x is positive. And L starts from 0. So increments of x are equal to increments of w if x is strictly positive, and f of L is a compensating process. So sometimes when the process is at 0, L may increase, f may increase, and a process x can reflect, maybe continuous sometimes, maybe by a jump. And moreover, we found a formula for x. So if f was this function and f was, okay, two additional conditions, f of 0 is 0 and f is unbounded, then we found a formula we didn't found, I stated a theorem that L of t is equal to generalized inverse of f and the running minimum of of w. So m of t is minus minimum of w of s minimum 0. And x was the sum w plus this. So x of t is w of t plus f and generalized inverse of f and composition with m of t. So we have, okay, so this is generalized, this is Skorokhod generalized map. Moreover, it can be proved that if these conditions hold, then this pair x and L is a unique solution to this problem. And now let's consider the following general question. Assume now that W and F are stochastic processes, and assume that we consider a sequence of stochastic processes W and F, and such that they converge in some sense to a limit process W and F as n goes to infinity, and assume that all processes Fn and Wn and W and F satisfy these conditions. We we may consider processes xn of t that are equal wn of t plus composition fn and generalized inverse and running minimum. And the question is it true that xn converges to x as n goes to infinity in some sense? Well, I write here convergence in distribution, but I have not written the metric space. Well, it may be, for example, space of Cadillac functions with Skorokhod topology times second coordinate d 0 infinity. Uh, okay, this space actually is separable, and let us discuss what are the ways. So, how can we prove these convergence? Well, let's apply Skorokhod representation theorem. Since this process is separable, then there are copies W and Fn with tilde of this pair, and a copy of this WF, a copy of this process, such that these processes converges to this process almost surely in the topology of this space, such that Wn tilde Fn tilde converges almost surely to. And now we fix omega, and we have deterministic question. We know convergence, this convergence. Is it true that xn tilde, which are constructed by this formula, converges almost surely to x? So is this map continuous? The answer is no. So let me write like exercise that find an example of non-random functions of functions Wn Fn such that this converges to Wf, but of deterministic functions, but Wn plus composition of this does not converge to W plus this. I also would like you to warn that if you find this example, then f must be discontinuous. Well, if all fn and f are continuous and strictly increasing functions, then this composition is just identity. And if you have convergence W to N to W, And if you assume that, and we have assumed that W is continuous, then we have uniform convergence, then we have uniform convergence of these running minimums, and then we have uniform convergence Wn plus Mn to W plus M. So if you wish to find a counterexample of this situation, then this function, then you have to consider discontinuous functions. Today I will formulate without proofs certain class of results, and that show that under very general conditions you get, actually you have convergence. So this counterexample is rather exception than a rule. And then I will formulate a few results about perturbation of random walks and their limits, and their limits will be Skorokhod reflections. Okay, the first result. So this result is deterministic. So theorem. Let Wn, Fn, W, F be catalog functions such that first, okay, Wn0, W0 are non-negative. Fn of 0 is F0 at 0 are non-decreasing, unbounded. The second, Wn converges to W and Fn converges to F as n goes to infinity in Skorokhod space. The third condition, this limit function W is continuous. And this limit function is strictly increasing. As in theorem of existence and uniqueness of a solution to the generalized Skorokhod problem. Actually, if we know that W is continuous, then this convergence is uniform. I will write the last condition, the last technical condition a little bit later. Then Wn plus composition of Fn and generalized inverse and the running minimum of W converges to W plus F composition with generalized inverse and M in Skorokhod space. So you see, these three conditions are very natural. So convergence, W and F are like in Skorokhod, in the theorem about on existence and uniqueness. Well, these are technical conditions that all functions are non-negative and bounded, so it's very natural to assume. And the fourth condition is this. For every point u0, a point of jump of this function such that there is at most one solution t0 of the equation. The running minimum of W at point t0 is equal to f of u0 minus. So, as I told you, generally, Skorokhod, generalized Skorokhod reflection is not continuous map, but it is continuous at point WF that satisfies this condition plus this technical condition. Maybe some fact or exercise again without a proof. If W is a Brownian motion, and f of t is any strictly increasing Cadillac and unbounded Cadillac and strictly increasing Cadillac process that is independent of Brownian motion is any strictly increasing that is independent of Brownian motion, then condition 4 is satisfied. And immediate corollary, okay, let me, yes, please.
Of t greater or equal than 0?
Oh, no. W of t greater than or equal to 0 is a Brownian motion. Thanks. So, if corollary from this theorem and this reasoning based on the Skorokhod representation theorem, we have the following result. So if Wn, Fn be a sequence of stochastic processes of Cadillac stochastic processes such that Wn, Fn converges to W and F, where W is a Brownian motion and F is independent of W such that these two coordinates are independent. And F must be strictly increasing and unbounded. The sequence is such that you have this, Fn are non-decreasing, F is strictly increasing, Fn are unbounded almost surely, and start from 0, and Wn of 0 are greater than or equal to 0. Then you have convergence in distribution, Wn plus this composition to the process W plus F generalized inverse and M. So what is the proof? We consider copies, such that we have convergence almost surely. Then for copies, we have convergence almost surely. Then we say that this sequence has the same distribution as this sequence, and for this sequence you have almost sure conditions. So for original sequence, we have convergence in distribution. You may ask me why? Because what does convergence in distribution mean? You take any continuous and bounded function of this process and expectation, and expectation must be convergent to expectation of a limit. Since they have the same distribution, then they have the same expectations. So we have indeed a convergence in distribution. Well, there are a few points that should be at least mentioned. I consider here inverse process and composition of processes. The question is composition measurable? Is some measurable function? And the answer is for such process is yes. Is yes. And now I also want to formulate without the proof a result on convergence of perturbed random walk. Assume that psi is that increments above 0. Consider the following random walk. Increments above 0 are equal to psi. So consider. And if you jump below 0, you have another increments that have distribution eta. When you enter positive side, again, the increments have the distribution as certain random variable xi, and when you jump below 0, there again eta. And okay, so let me, so oops, so here distribution xi1, say xi2, xi3. This increment is eta 1, eta 2, oops, xi4, xi5, xi6, eta 1, eta 2, eta 3, eta 4, eta 5, and so on. We assume that expectation of xi is 0, variance of xi is 1, and eta some other random variables that are non-negative. So I wish to have eta such that they push our process above. So let xn be a Markov chain such that its transition probabilities are the following. So it jumps from, if x is positive, then probability that you jump from xi to y is equal to probability that xi is equal to y minus x. Oh, we considered, okay. Okay, consider for simplicity integer valued random variables, and if x is negative, then the distribution of jump is equal to eta. And we assume that eta greater than 0, almost sure. Now let's consider Donsker scaling limit of x, and Donsker scaling, and the question is, what is the limit of this scaling of this random walk? Well, let t a of n be the number of xi's used before the instant n, the number of jumps above 0 when we use xi, and tbn is the number of jumps below 0. And well, assume that x0 is greater than 0, then the first jump will be xi, and xi introduce two random walks as xi and as eta, like x0 plus xi1 plus xin, and here eta 1 plus eta n. And now you see what is xn. is initial position plus number of jumps plus sum of xi1, xi2, xi3, xi4, xi5, and you have to use the number ta of n. So, and plus increments where increments have distribution etas. So xn can be written as xi of ta of n plus s eta tb of n. And consider the scaling. As S eta tb n t divided by square root of n. Let me here multiply by n, divide by n. Well, and the question is, what is the limit? Well, we know that s psi of nt divided by square root of n converges in distribution to a Brownian motion. Well, you have here dA of nt, and it's interesting to know. It's interesting to know, is this amount dA of nt large or not? So how often you use the jumps xi and how often you use the jumps eta? It can be shown that always Ta of nt divided by n converges to t as n goes to infinity. Almost surely, and moreover uniformly, locally uniformly. So this is non-trivial result, but assume that you know it. Then you may apply Skorokhod representation, and the immediate consequence of this will be that this is a Brownian motion. Well, assume that you have copies, and on some probability space, copies converge to a Brownian motion almost surely. Oh, now, well, I don't know if the limit exists, but assume that the limit exists. Will it be non-negative? And the answer is yes. Why? What is the minimal value of this random walk x? So it is greater than or equal to minimal jump, because we assume that etas are positive. And since xi's have the second moment, then for every n, maximum of psi k less than nt divided by square root of n converges to in probability to 0. We discussed this. So if the limit of this sequence exists, then, okay, we know that the limit of this exists. Then the limit at first will be non-negative. It will be Brownian motion plus something non-decreasing, something non-negative, and you see, you use these jumps only when the sequence is less than or equal to 0. And if sequence x is positive, you do not use jumps eta. So probably the limit, if it exists, it will be some kind of Skorokhod reflection. Skorokhod reflection. And well, it's natural to consider eta such that scaling limit of eta exists. So assume that Sn of nt, well, I don't know, should I divide by square root of n or should I divide by another sequence? Converge in distribution under some scaling to a certain process. Where n is a sequence of non-negative numbers such that limit of n is plus infinity. And f and f is Cadillac process, and strictly increasing. Or assume that, you see, here scaling is square root of n. So we may assume, okay, that there is some sequence Bn of t such that you have convergence to certain process, this or this. For example, divide by not Bn, but divide by square root of n. And now consider this term. So my aim is to guess the answer. Well, let me multiply by Bn, divide by Bn, and observe that if this process has a limit, then Sn of Bn divided by square root of n should converge to composition of, so if these converge in some sense, maybe almost sure, or in distribution to some process A, then this should converge to, okay, this is just guess, to a composition F and L. And now what will we return back? And we consider this sum. Oh, what should a limit be? It should be W plus F and L. And this process do not increase if the limit is positive. So if sequence eta is quite nice, and if we are able to prove this convergence, then the limit of perturbed random walk should be Skorokhod reflected process. Okay. And now the question. So what are the possibilities for f of t? So just general question from probability theory. Find conditions on eta such that s eta of n divided by an, just consider eta 1 plus eta 2 plus eta n. So let me write, okay, s eta of n divided by an. Describe all etas and sequences in such that this sequence converges in distribution to a non-trivial random variable. And my question is, can you describe at least some etas and some sequences an such that such limit exists?
Yes, if we take eta not big and an, for example, n square, we get 0.
Yes, but my question is non-trivial random variable.
Okay, sorry.
So non-trivial limit. So non-zero
Okay.
limit. Okay.
Then the law of big numbers.
Of large numbers. Yes. Yes. The first example is if expectation of eta is finite, then eta 1 plus eta n over n. Well, we have not only convergence in distribution, but almost sure convergence, and you have convergence to a constant. So now an is n. Another example, yes, so this is law of large numbers. Yes, the second example is the central limit theorem. If expectation of eta is 0 and variance of eta is sigma squared, then if you take an is square root of n, then you have convergence in distribution to the normal distribution. Okay, maybe you have heard about other types, other etas and their limits.
Stable distributions.
Yes, stable distributions. Stable distribution. Uh, oh, and okay. There are two definitions, but equivalent definitions of a stable distribution. So random variable eta, so definition 1. So eta has a stable distribution. If for every n there are constants an and bn, such that eta 1 plus eta 2 plus eta n minus an divided by bn has the same distribution as eta. And eta 1, eta 2, eta n are copies of eta. And the distribution is called strictly stable. If an is 0. So if you have a strictly stable distribution, an is 0, then okay, let me write here minus bn divided by bn divided by an. Then you have not only there is my definition. Then you do not have a convergence, but even you have equality. Eta 1 plus eta 2 plus eta n divided by an is equal to eta. Well, sometimes people use another definition. So eta, but equivalent, it can be proved that the definition is equivalent, has a stable distribution. If there are sequence of zn of id random variables and sequences cn and dn such that zeta1 plus zeta2 plus zn minus cn divided by dn converges to eta. So in some sense, so stable distributions are the only distributions that can be obtained as a limit of scalings of random walks. It's also known, so let me just give references. So you may read, for example, book by Kallenberg, Foundations of Modern Probability. Foundation of Modern Probability. Or, for example, a book of Feller, Introduction to Probability Theory and its Applications, Volume 2, or by a book by Gnedenko and Kolmogorov, where you can find comprehensive study of limit theorems and results and characteristic functions of and description of all stable distributions. Well, it appears that these A, N, and Dn are not arbitrary, but have certain special properties, and if eta has a stable distribution, then its characteristic function has the following form. Then there is a parameter alpha in 0, 2, such that characteristic function of eta has the form exponent of I alpha z minus sigma squared z squared over 2 if alpha is 2. Oh, a z, and this is Gaussian random variable, and in this case this sequence an is square root of n, or in the case alpha in 0, 2, characteristic function has this form exponent IAZ. Well, e to the power IAZ is just a constant, characteristic function of a constant, plus integral over r, one constant c minus times indicator that x e, excuse me, x z minus 1 minus ix z indicator that x less than 1 nu dx, where measure nu is the following: a constant c minus times indicator that x less than 0 plus a constant c plus times indicator that x greater than 0 times dx divided by absolute value x raised to the power 1 plus alpha. Well, if you studied Levy processes, then you see that if you subtract here minus sigma squared z squared over 2, then this is Levy-Khinchin representation of characteristic functions. For stable processes, measure nu, so-called Levy measure, has the following special form, and constant c plus and c minus are non-negative, and at least one of these constants should be positive.
Excuse me, what
Mhm.
is written in first line expectation? Is that A or what is that letter?
Yes, E, A, Z, yes, yes. The
And
normal
what is
distribution.
what is A?
Any number. A is
Uh,
any number, sigma squared is any positive number. And here A is any number, and C plus and C minus are non-negative.
okay, thank you.
And moreover, the scaling sequence an in the definition is n to the power 1 over alpha. So if alpha is square, if alpha is 2, then you have Gaussian distribution and square root of n, but for general case, it's this. Well, so uh, if we assume that certain scaling limit of sequence as eta is non-trivial, then it can be shown that the only possibilities is processes that have stable distributions. Moreover, Sn so S eta of n, so it is natural to suggest that this process will be a process with independent increments such that one-dimensional distributions are stable and and non-negative. Non-negative because we assume that etas are non-negative random variables. Well, again, the question is how to describe all non-negative stable processes or so-called stable subordinators. And the question is how to describe all non-negative stable distributions. And the answer is this. Well, Gaussian is impossible. Alpha between 1 and 2 is impossible. C minus should be 0. And eta is non-negative stable random variable if and only if there is alpha between 0 and 1, C plus greater than or equal to 0, A greater than or equal to 0, such that characteristic function of eta has the following form. Exponent of I A Z plus integral from 0 to infinity I x z minus 1 c plus dx x to the power 1 plus alpha. You may say, well, you forgot about this indicator and integral of I x z. And my answer is no, I don't forget. If alpha is between 0 and 1, this x can be is integrable with respect to this measure. And if you integrate it, you obtain I times z times some constant. And well, when you rewrite the formula, you just obtain a new A. Okay, again, this fact is without proof. Without proof. Sometimes it's easier to consider Laplace transforms of eta instead of characteristic function. And the Laplace transform is this. So lambda is non-negative parameter. Exponent minus lambda a minus some constant, may be different from C plus, times lambda to the power alpha. Well, actually, this integral also can be calculated, and you will see z to the power alpha with additional constant, but this constant is, oh, excuse me, here some constants. But after integration, the corresponding constant has a terrible form. You may find all this constant in the cited books. Well, so we have nice description of stable random variables, and my next question is, well, how to prove the theorem? How to prove weak convergence? So I'm not going to prove. I just go. I just want to recall the way. Well, how can we prove certain convergence in distribution of random variables? Well, there are few ways. The first, verify the definition, which is terrible. The second, you may show convergence of distribution functions in all points where the distribution function of a limit is continuous. Well, I have doubts that it's possible to find nice formulas for distribution functions if zeta is non-trivial random variable, except of very special cases. And the third way is the usage of characteristic functions. So we know that convergence in distribution is equivalent to convergence of characteristic functions. Well, and let's ask ourselves, so my aim is to find conditions when you have this without subtracting something. And well, characteristic function of this random variable is equal to e to the power I z this sum. And you have independent identically distributed random variables. So expectation of product of exponents is equal to product of expectations. And finally, all random variables they have same distribution. So the answer is zeta. And this will be characteristic function of that at the point z divided by Cn to the power n. Well, and Cn, the scaling constant should goes to infinity. So z over Cn converges to 0. So characteristic function converges to 1 and n converges to infinity. So the limit is like 1 to the power infinity. So uncertainty. So what are we doing in this case? We add 1, we subtract 1. We raise to the power 1 over phi zeta z Cn minus 1. We multiply and divide. And this converges to E. And if there is a limit as n goes to infinity, n times characteristic function of zeta z over Cn minus 1. And if this function is continuous at 0, then you have convergence to e raised to the power psi of zeta. So in order to prove limit theorems, you need to know asymptotic of characteristic function in a neighborhood of 0. So if you have nice asymptotic of characteristic function in a neighborhood of 0, then you can prove, or then you can find scaling limits of zeta. Relation between, okay, the reasonable question is, what is sufficient or necessary and sufficient conditions that characterize behavior of characteristic function in a neighborhood of 0? Well, there are so-called abelian and tauberian theorems that state that characteristic function has, say, power asymptotic in the neighborhood of 0 if and only if tails of the distribution of zeta have, say, like power asymptotic in the neighborhood of plus and minus infinity. Well, again, the reference is Gnedenko-Kolmogorov book or Feller book, volume 2, where you may find all of these results. But this is the answer. So this is at least a way of proof or way of investigation of scaling limits. And assume that you have this convergence of random variables. And we return back. If you have convergence of scalings to a certain random variable, what about processes? If we have convergence of one-dimensional distribution, do we have convergence of processes or not? And the answer is yes, in the case of random walks. So it can be proved that if zeta1 plus zn over Cn converges to a limit, let me say tau, which is necessarily a stable distribution. With certain parameter alpha, then these processes divided by Cn with the same scaling converges to alpha stable process where the distribution of the process at the point 1 has the same distribution as tau. This is non-trivial result. This is non-trivial result proved by Skorokhod. You may find the proof of this result, for example, in the book by Kallenberg that I mentioned. And now, again, the final result. So we guessed the limit, we say that, well, if we consider this random walk with increment psi above 0, with increments eta below 0, and if the theorem is this. So if expectation of psi is 0, variance of psi is sigma squared, and if eta is non-negative, and eta belongs to domain of attraction of stable law, this means that some scaling of eta converges to a non-negative stable random variable. Eta belongs to a domain of attraction of alpha stable law. Well, and alpha automatically between 0 and 1. Then scaling of x converge to Skorokhod reflection, generalized Skorokhod reflection, Brownian motion plus U alpha and U alpha inverse and the running minimum of a Brownian motion, where W is independent of U alpha and convergence in Skorokhod space D of Kadlak functions. So intuition gives us the result. And I also wish to formulate one more result that is close to this one. And the result is the following. Let's consider, so W is a Brownian motion. Let W is a Brownian motion started from certain point X that is non-negative. Consider a process xt that has the following form. And xik are IID, and everything is independent. So at first you have a Brownian motion until you hit 0. Then you jump, and the first jump is xi1, and then again you assume that increments are increments of this Brownian motion until the second hit of 0, and again you make jump xi3 and so on and so forth. You come, jump, and we denote this process as xi. Well, you can write xi as the following: W of t, Brownian motion, plus sum of jumps. Sum of jumps, n of t, where n of t is the number of jumps before times t. And now let's make jumps smaller and smaller and consider the process as xi over nt. So the first jump will be xi1 divided by n, the second xi2 divided by n, the third xi3 divided by n, and so on and so forth. I forgot to mention, assume that xik are non-negative. And the question is, what is the limit of this process as n goes to infinity? Maybe I have to write here eta to be consistent with previous example. And the result is the following. If eta belong to domain of attraction of alpha stable law with alpha in 0, 1, then this sequence converges to the process that we discussed in the previous theorem. And if this eta have finite expectation, then the sequence of these processes is usual Skorokhod reflection. Well, in some sense, the scaling of eta 1 plus eta 2 plus eta n so in this case, if you consider this sequence, then the limit will be just constant time t, where a is expectation of eta. And so this is analog of this function, and inverse is t divided by alpha, and composition is just identity. So this can be considered as a limit case of this one. I also do not prove this theorem, but you see that Skorokhod reflection appears naturally as the limit of models with perturbation. And at first we guessed the answer that, well, if you have something regular that is close to Brownian motion above, non-negative, and if jumps from 0 converge to a nice process, well, under certain scaling, then the limit is Skorokhod reflection. And moreover, we discussed that the only possibility for scalings of S eta can be alpha stable processes, and well, or linear function, and that's all. So this is the end of my lecture, and next time I'm going to consider the case when perturbation in a neighborhood of 0 is two-sided. With certain probability, you can reflect up, and with a certain probability, you can reflect down. So in this case, we do not have Skorokhod map or Skorokhod reflected map, and the question is how to describe limits, how to what are the ways of proof of convergence, how to guess a limit, and so on and so forth. To say the truth, I have not proved theorems about generalized Skorokhod reflection. Only I proved I considered the case only with classical Skorokhod reflection. It was easier. The reason for this is, well, to consider convergence in space D, in Skorokhod space, you have to work. It's not usual convergence. It is not uniform convergence. So the questions on continuity of inverse map, of composition, of sum in Skorokhod space is very delicate. So all of this stuff should be used in the proof of these theorems. To understand when composition or inverse or sum is continuous, I recommend you to have a look at a book by Witt. And the title of book is, one moment, stochastic processes limits. Stochastic processes limits, an introduction to stochastic processes limits and their applications to Qs. He has a chapter that is called Useful Functions, where he considered continuity of inverses, of composition, sum, and so on and so forth in various topologies. Okay, that's all for today. Thank you for your attention.